Claims about the true shape of the Earth being hidden or altered have been investigated repeatedly. And in every verified case, the data satellite measurements, geodesy, and physics converge on the same conclusion within margins of error measured in centimeters. This is the life story, not of a secret map, but of a doctrine. The idea that institutions conceal fundamental truths, and how that idea forms, spreads, peaks, and eventually reveals more about human perception than about the planet itself, a lesser known. Fact is that early geodetic surveys in the 18th century already measured variations in Earth's curvature due to equatorial bulging, a design compromise of nature that produces an oblate spheroid rather than a perfect sphere. Its birth begins with a problem older than any intelligence agency. Humans struggle with scale. The Earth is too large to perceive directly, and so its shape must be inferred through instruments, mathematics, and indirect observation. That gap between perception and reality creates space for doubt, a lesson. Fact is that early measurement expeditions, such as those comparing meridian arcs, produced discrepancies of several hundred meters due to instrument limitations, a test result that initially fueled uncertainty rather than clarity. The parents of the doctrine are not organizations like Central Intelligence Agency, but rather the intersection of mistrust, complexity, and selective information. Cold War secrecy amplified this environment. And all it took was a single shiny object, that one lucky child found, in order to change the future, but rather the intersection of mistrust, complexity, and selectivity. Satellite programs, classified imagery, and restricted data access created conditions where absence of information could be interpreted as concealment. A lesser-known fact is that early satellite reconnaissance programs classified nearly 90% of collected imagery, a supply constraint of information that limited public access for decades. Early forms of the idea were inconsistent. Some suggested a flat Earth, others a hollow one, others distortions hidden by maps. These were not unified theories, but fragments, shaped by misunderstanding of projection systems and limited exposure to scientific data. A lesser-known fact is that common map projections, such as Mercator, distort landmass size significantly, a design compromise that can exaggerate regions near the poles by over 200%. Childhood of the doctrine was marked by repetition without verification. Claims circulated without supporting evidence, often relying on anecdote or reinterpretation of existing data. Training in scientific literacy among the general public varied widely, affecting how such claims were received. A lesser-known fact is that studies in science education show that misunderstanding of scale and projection persists in over 30% of surveyed populations, indicating a crew training detail gap in foundational knowledge. Small changes in communication had large effects. The rise of mass media allowed ideas to spread faster, but not necessarily more accurately. Visual content, in particular, could reinforce misconceptions if not contextualized properly. A lesser-known fact is that visual misinformation is retained by viewers up to 6 times more effectively than corrected textual explanations. A psychological effect influencing belief, persistence, misunderstandings often centered on real phenomena. The Earth is not a perfect sphere. It has irregularities, mountains, trenches, gravitational variations. These complexities were sometimes misinterpreted as evidence of hidden structures. A lesser-known fact is that the geoid, a model of Earth's mean sea level, varies by up to 100 meters globally due to gravitational anomalies. A terrain impact that complicates simple descriptions of shape. Growth of the doctrine accelerated with digital communication. Online platforms allowed communities to form around shared beliefs, reinforcing ideas through repetition. Algorithms prioritized engagement, sometimes amplifying extreme or unusual claims. A lesser-known fact is that engagement-driven algorithms can increase visibility of niche content by over 50% compared to baseline distribution, a production issue of information systems. Standardization within these communities emerged. Common arguments, shared sources, and repeated narratives created a structure resembling doctrine. It was not coordinated, but it was consistent. A lesser-known fact is that repeated exposure to identical claims increases perceived credibility by approximately 20%, a psychological effect known as the illusory truth effect. At its peak, the doctrine gained visibility beyond its core adherents. Public debates, media coverage, and responses from scientific institutions brought it into broader awareness. The idea of hidden truth became more prominent than the specifics of the claim. A lesser-known fact is that public engagement with controversial scientific claims can spike by over 300% following media coverage. Regardless of accuracy, a defining scenario is not a battlefield, but a discussion. A claim is presented. Evidence is requested. Data is provided: satellite imagery, GPS measurements, physics models. The doctrine does not collapse under evidence. It adapts by reframing the source as untrustworthy. A lesser-known fact is that belief systems can incorporate counter-evidence by redefining its origin, a countermeasure that preserves internal consistency. Why does it work in that context? Because it simplifies complexity. A single hidden truth is easier to grasp than a network of measurements, models, and uncertainties. It offers certainty where science offers refinement. A lesser-known fact is that cognitive load increases significantly when processing complex scientific data, leading individuals to prefer simpler explanations even when less accurate. The cost is not physical, but cognitive and social. Time and attention are invested in maintaining belief systems that resist correction. Discussions become polarized. Trust in institutions can erode. A lesser-known fact is that erosion of institutional trust correlates with decreased acceptance of scientific consensus by measurable margins in survey data. Fatigue appears in different form. Constant evaluation of information, defensive positions, and engagement in debate create mental strain. The doctrine demands vigilance, but a belief rather than territory. A lesser-known fact is that prolonged engagement in adversarial discussions can increase stress markers, including elevated heart rate and cortisol levels. There are also indirect effects. Misunderstanding of Earth's shape can influence interpretation of navigation, climate science, and space exploration. The impact extends beyond the original claim. A lesser-known fact is that misconceptions in one scientific domain can reduce comprehension in related domains by up to 15%, indicating interconnected knowledge structures. Old age of the doctrine does not mean disappearance. It persists, but with reduced novelty. New claims replace old ones. Focus shifts. The core idea of hidden truth remains, but its expression evolves. A lesser-known fact is that long-standing fringe theories often maintain a stable core audience, even as public attention fluctuates. Replacement comes not through elimination, but through integration of better tools. Increased access to data, improved education, and transparency in scientific processes provide alternatives. A lesser-known fact is that open-access satellite data programs have expanded significantly, with thousands of data sets now publicly available. For independent analysis, new doctrines emerge, often unrelated in content but similar in structure. The pattern repeats: complexity, mistrust, simplification, reinforcement. The specific claim changes. The mechanism does not. A lesser-known fact is that patterns of belief formation show consistent structures across unrelated topics, suggesting underlying cognitive processes. Its legacy is not about the Earth. The shape of the planet is measured, tested, and confirmed through multiple independent method satellites, gravity measurements, and direct observation. The legacy is about how humans interact with information. A lesser-known fact is that modern geodesy can measure Earth's shape with precision to within centimeters using satellite laser ranging and GPS networks. What later systems learned is not how to hide truth, but how to communicate it. Transparency, accessibility, and education become as important as data itself. A lesser-known fact is that public engagement initiatives in science increase trust metrics by measurable percentages when sustained over time. And so the doctrine settles into a quiet state, not gone, but understood, not dominant, but persistent. It remains as a reminder that uncertainty invites interpretation, and interpretation does not always follow evidence. A lesser-known fact is that uncertainty in scientific communication, when not clearly explained, can lead to misinterpretation in a significant portion of audiences. The Earth remains what it is, an oblate spheroid shaped by rotation and gravity, measured continuously, understood progressively. The fear lies not in its shape, but in the distance between what is known and what is believed. Roughly 31 active GPS satellites orbit at altitudes near 20,200 kilometers, and each one depends on timing, precision, measured in billionths of a second, to map position on a rotating, slightly flattened planet. What follows is a continuation of a doctrine that did not collapse under measurement, but adapted around its shifting focus from what can be tested to what can be doubted. A lesser-known fact is that satellite clock drift must be corrected for relativistic effects of both velocity and gravity, a test result that confirms predicted physics within nanosecond tolerances. The next phase unfolded as access to data expanded. High-resolution imagery, publicly available orbital trackers, and consumer-grade GPS devices placed tools of verification into ordinary hands. In theory, this should have reduced uncertainty. In practice, it created a new layer interpretation of data without shared standards of understanding. A lesser-known fact is that raw satellite datasets often require specialized calibration procedures, a production issue that can lead to misinterpretation if used without context. Different communities began to construct parallel frameworks of explanation. The same image could support multiple conclusions depending on assumptions about scale, projection, and source reliability. Agreement on data did not guarantee agreement on meaning. A lesser-known fact is that ambiguity in visual data increases divergence of interpretation by measurable margins in controlled studies, a psychological effect tied to prior belief structures. Small, technical details became focal points. Lens distortion, stitching of panoramic images, compression artifacts each could be isolated and presented as evidence of manipulation. These details were real, but their implications were often expanded beyond their actual significance. A lesser-known fact is that Wodongo lenses can introduce barrel distortion of up to 5 to 10% at image edges, a design compromise inherent in optical systems. Efforts to counter these claims relied on demonstration, weather balloons, amateur rockets, and long-distance photography projects attempted to replicate observations independently. Results were consistent with established models, yet acceptance depended on trust in method as much as outcome. A lesser fact is that high-altitude balloon experiments routinely reach altitudes of 30 kilometers, where curvature becomes detectable within expected geometric limits, a test result reproducible by non-institutional groups. The doctrine adapted again. Instead of rejecting all data, it began to filter. Certain sources were accepted, others dismissed. Criteria for acceptance were not always explicit, but they created a closed loop of validation. A lesser-known fact is that selective trust mechanisms can reduce cognitive dissonance by limiting exposure to conflicting information, functioning as a countermeasure within belief systems. At its operational peak, the doctrine became less about the Earth itself and more about authority. Institutions were reframed as gatekeepers rather than sources. The question shifted from what is true to who controls what is presented. A lesser-known fact is that shifts from content-based to source-based evaluation represent a command doctrine change in how information is processed. A defining moment in this phase often appears as a technical debate. Orbital mechanics are explained. Calculations of curvature over distance are shown. The response does not necessarily engage the numbers. It questions the framework in which those numbers exist. A lesser-known fact is that orbital predictions, based on Newtonian mechanics, can achieve positional accuracy within a few kilometers over thousands of kilometers, confirming model reliability. Why does it persist in that form? Because it reduces the burden of verification. If the framework is dismissed, individual data points no longer need to be reconciled. The system becomes internally consistent by design. A lesser-known fact is that rejecting foundational premises can simplify reasoning processes, reducing cognitive load at the expense of accuracy. There are measurable social effects. Conversations become less about shared inquiry and more about defensive positions. Common ground narrows. The doctrine, in seeking certainty, can produce fragmentation. A lesser-known fact is that polarized discussions reduce likelihood of consensus by over 40% in experimental settings, indicating structural barriers to agreement. Individuals within the system often develop high familiarity with specific arguments, data points, and counterpoints. Expertise, in a limited scope, increases. Broader integration of knowledge, however, may decrease. A lesser-known fact is that domain-specific knowledge, without cross-domain integration, can lead to overconfidence in conclusions. A documented cognitive bias. Fatigue manifests differently. Here, it is not physical exhaustion, but informational saturation. Continuous exposure to conflicting claims creates a sense of overload, leading some to disengage entirely. A lesser-known fact is that information overload can reduce decision-making accuracy by up to 20%, particularly in complex or contested domains. Meanwhile, scientific systems continue to refine measurement. Satellite constellations expand. Laser ranging improves precision. Models of Earth's shape incorporate more variables, reducing uncertainty incrementally. A lesser-known fact is that modern Earth observation systems can detect surface changes on the order of centimeters, demonstrating increasing resolution. Over time, the gap between systems widens. One side accumulates precision, the other stabilizes around core assumptions. Interaction between them becomes less frequent, and when it occurs, less productive. A lesser-known fact is that sustained divergence in belief systems can lead to parallel information ecosystems with minimal overlap. Over time, novelty fades. The claim no longer shocks. It becomes one of many competing narratives. Attention shifts elsewhere, but the structure remains, ready to be applied to new topics. A lesser-known fact is that attention cycles for controversial topics typically decline after initial peaks, but baseline engagement often remains above pre-exposure levels. Replacement does not erase the doctrine. It repurposes it. The same mechanisms questioning authority, simplifying complexity, reinforcing internal consistency appear in different contexts. A lesser-known fact is that transferable cognitive frameworks allow belief structures to adapt across unrelated subjects with minimal modification. Its legacy becomes clearer in hindsight. Not a revelation about the Earth, but a case study in interpretation, a demonstration of how data, trust, and perception interact under conditions of uncertainty. A lesser-known fact is that interdisciplinary studies of misinformation identify recurring patterns regardless of topic, suggesting common underlying processes. What remains constant is the planet itself. Measurements converge. Models align. Independent systems from navigation to climate science depend on the same underlying geometry and confirm it continuously. A lesser-known fact is that global navigation systems rely on consistent Earth models to maintain positional accuracy. Within meet is a practical validation of theoretical shape. The doctrine, however, leaves its imprint. It influences how questions are asked, how answers are evaluated, and how certainty is constructed. It does not disappear. It becomes part of the landscape of thought. A lesser-known fact is that long-term exposure to alternative explanatory frameworks can alter baseline skepticism levels in measurable ways. And so the story continues, not as a conflict between truth and falsehood, but as an ongoing negotiation between evidence and belief. The Earth turns, measured and remeasured. While the distance between knowing and accepting remains a variable no instrument can fully close. Nearly 2,000 active Earth-observant instruments now feed continuous streams of data into public and private systems, each one measuring curvature, gravity, or orbital motion with independent methods that converge on the same model. The doctrine does not end when evidence accumulates. It shifts again, adapting to a world where verification is no longer rare but constant. A lesser-known fact is that cross-calibration between satellite systems reduces measurement error by up to 35%. A production issue of harmonizing data from different instruments in this later phase, scale becomes a central challenge once more. The amount of available information grows faster than the ability of individuals to process it. Data that once required institutions is now accessible on personal devices, but interpretation still demands training. A lesser-known fact is that the volume of publicly available Earth observation data has doubled approximately every 5 to 7 years, creating a supply constraint in human analytical capacity rather than data availability. Different responses emerge to this overload. Some move toward deeper specialization, learning the details of geodesy, orbital mechanics, and remote sensing. Others simplify further, relying on trusted summaries or familiar narratives. The divergence increases not because of lack of data, but because of different strategies of handling it. A lesser-known fact is that specialization in technical fields can require thousands of hours of focused study, a crew training detail that limits widespread expertise. Small technological shifts have large effects. Real-time visualization tools allow users to see satellite paths, weather systems, and planetary curvature dynamically. These tools make abstract concepts more tangible, but only if used with understanding of their assumptions. A lesser-known fact is that visualization software often applies smoothing algorithms that can alter raw data adherence, a design compromise that prioritizes clarity over strict fidelity. Attempts at reconciliation appear periodically. Educational initiatives, open data platforms, and collaborative projects aim to bridge gaps in understanding. Success varies. Engagement depends not only on access, but on willingness to participate. A lesser-known fact is that interactive learning environments improve comprehension of spatial concepts by up to 28%. According to educational research, at the same time, counter-narratives refine their methods. Instead of broad claims, they focus on specific anomalous edge cases, unexplained measurements, or rare inconsistencies. These become focal points for discussion, even when they fall within expected margins of error. A lesser-known fact is that measurement systems inherently include uncertainty ranges, often expressed as confidence intervals, a test result characteristic that can be misinterpreted as inaccuracy. A defining scenario in this stage often unfolds quietly. An individual downloads raw satellite data, attempts analysis, and encounters complexity coordinate systems, calibration constants, atmospheric corrections. The barrier is not secrecy, but technical depth. A lesser-known fact is that atmospheric refraction can alter apparent positions of objects by measurable degrees, a weather and terrain impact that must be corrected in precise calculations. Why? The doctrine continues to find space is not because of absence of answers, but because of abundance. Too many details can obscure the core. Simplicity regains appeal. A lesser-known fact is that decision-making under high complexity often reverts to heuristic shortcuts, reducing cognitive load but increasing risk of error. The human cost remains subtle but persistent. Continuous exposure to conflicting interpretations can erode confidence in one's own ability to evaluate information. Some disengage. Others double down on chosen frameworks. A lesser-known fact is that repeated exposure to unresolved conflict and information sources can increase anxiety levels and reduce perceived control. Communities form around shared approaches to knowledge. Some emphasize verification, replication, and peer review. Others prioritize independence from institutional frameworks. Both provide structure, but lead to different outcomes. A lesser-known fact is that peer-reviewed scientific processes include multiple stages of validation, reducing error rates through collective scrutiny. Fatigue evolves into selectivity. Individuals choose which sources to trust, which topics to engage with, and which to ignore. The doctrine becomes less about a single claim and more about a general stance toward information. A lesser-known fact is that selective exposure to information can reinforce existing beliefs by up to 25%, according to behavioral studies. Meanwhile, measurement systems continue without interruption. Satellites orbit, ground stations track, data accumulates. The physical model of the Earth is refined incrementally, not dramatically. A lesser-known fact is that tectonic plate movement is measurable at rates of centimeters per year, demonstrating the sensitivity of modern geodetic systems. The gap between system scientific and interpretive stabilizes us. It does not close, but it becomes predictable. Each operates according to its own rules, occasionally intersecting but rarely merging. A lesser-known fact is that stable divergence between information systems can persist for decades without convergence, particularly when reinforced by social structures. Over time, attention shifts again. New topics emerge, new uncertainties arise, and the focus of the doctrine moves with them. The underlying mechanism remains intact, ready to apply to different questions. A lesser-known fact is that patterns of belief adaptation allow rapid transition between topics while maintaining core reasoning structures. What remains from this phase is a clearer understanding of limits not of the Earth, but of communication. Data alone is not sufficient. Interpretation, trust, and context are equally important. A lesser-known fact is that effective science communication requires alignment of message, medium, and audience, with measurable impact on comprehension. The legacy of the doctrine settles into a quiet background. It becomes one example among many of how humans engage with complex systems, not unique, but illustrative. A lesser-known fact is that case studies of misinformation are used in training programs to improve critical thinking and analytical skills. The Earth continues unchanged in its fundamental, form-measured, modeled, and observed through independent systems that agree within defined margins. The doctrine, however, leaves a different imprint. A lesser-known fact is that convergence of independent measurement methods is considered a strong indicator of model accuracy in scientific practice. And so the story does not end with revelation or collapse. It resolves into coexistence of evidence and interpretation, of measurement and belief. The planet remains consistent, while the ways of understanding it continue to evolve.